So what we've been looking at in the previous lecture is the Poisson-Gamma conjugate case, and I showed you that we have to somehow figure out what the prior is on the lambda parameter for the Poisson likelihood, and we know that the gamma distribution is a reasonable probability density function we can use as a prior for the lambda parameter. But the interesting question now is how to figure out what A and B are, right? So what I showed you last time was that we have some prior knowledge, right? We are thinking about this hypothetical situation that we have some expert knowledge that tells us that the mean rate of regressions is 3 and the variance is 1.5. We also know that in a gamma distribution, the mean is A over B, where A and B are the parameters, and the variance is A over B squared. So it's a simple algebraic problem that can easily be solved. So I've got A divided by B, that's the mean of the gamma, equal to 3, and A divided by B squared is equal to 1.5, right? That's the variance that we know from prior research, right? So all you have to do now is, for example, equate A equal to 3 times B, plug it into this equation here. So I got 3 times B divided by B squared is equal to 1.5, and hopefully you can see that that implies that B has to be 2. So once I know that B is 2, I can plug it in here and I get A is equal to 6. Right? So that's it. I mean, I know I've done a principled analysis, to figure out what my prior parameters are going to be for the gamma distribution, and this is for the lambda parameter that I'm trying to work out, right? So if you maybe want to do this yourself once, maybe it's a good idea to try that out. Okay. All right. So this is what my prior is now, based on my prior knowledge, right? So this is what the prior looks like. I've got A and B parameters specified, and this is going to be my prior on the lambda parameter in the Poisson likelihood. Okay, so I'm simply going to multiply now. Okay, the rest of the steps are going to be just simple multiplication and addition. Okay, so what am I doing now? I'm going to figure out the posterior distribution of the lambda parameter in the Poisson likelihood, right? And I will do that by multiplying the likelihood and the prior up to proportionality. Why up to proportionality? Because I'm ignoring the normalizing constants. Okay. All right. So how does this work? So let's assume that we have n data points. So these are n independent data points which I'm representing as a vector. So that's what those angled brackets are supposed to mean. And so I'm writing x as a vector of values. That's why it's in boldface, in math boldface. Okay. So I've got n independent data points. So these are the regressive eye movements. Okay. So what I'm now doing is I'm figuring out the likelihood for all those n data points, the n independent data points, using the Poisson distribution, the probability mass function for the Poisson distribution. If you recall, the formula for the Poisson distribution was this thing here, where x is the data, right? So x is the data here, right? So all I have to do now to figure out what the probability of this vector of data points is to take each of those data points, x1 through xn, plug it into the Poisson likelihood, right? And multiply out each of those values with each other. Why can I multiply these out? Because they are independent values. So I've got n independent data points, and for each of the data points, I can figure out the probability of each data point. So I'm just calculating the joint probability of all these data points, right? And so that's what I've done here. That's it. Now this notation is very cumbersome because I have to write multiplication and then dots and multiplication. So what I did is I just wrote it out more compactly. Instead of the summation notation, I have a product symbol here, which just says the same thing as here, that for the n data points, I'm just plugging in the ith data point here, and I'm just multiplying those guys out. That's pretty much it, right? And so one thing to notice here is that this multiplication is pretty easy, right? Because I've got here, in this term here, I've got lambda to the power of x1. Then I've got in the next term, which I haven't shown here, I would have lambda to the power of x2. Then the next term would be lambda to the power of x3, all the way to lambda to the power of xn. Now what happens if I multiply these n terms out? I would get lambda to the power of the sum of all those x's, right? Because they're exponents, so I'm just adding them up, right? So that's why it's so simple. That's how I end up with lambda sum of x here in this calculation here. So what I'm doing right now, by the way, don't forget what we are actually doing. We are trying to compute the likelihood of the data, right? We're figuring out the likelihood, right? In terms of the parameter lambda, right? So given all the data. So that's how I end up with lambda to the power of sum of x, right? Similarly, the exponential term has exponential minus lambda once for the first data point. For the second data point, I will again get exponential minus lambda, and then all the way up to n data points. So that means I have n instances of exponent to the power exponent minus lambda. So what is that going to amount to? That's going to amount to exponent minus n times lambda, because I have n data points, right? So that's how I end up with this final term here, right? And at the bottom in the denominator, of course, I just have the products of all the x's, right? X factorials there, right? So that's how I end up with the likelihood of multiple data points, right? This is the closed form solution for the likelihood in terms of lambda, the parameter lambda in the Poisson for the data, right? The likelihood that I have from the Poisson distribution. Okay, so I have worked out what for multiple data points my likelihood is going to look like. Why do I need it? Because I'm going to plug it in here and multiply it with the prior on lambda, okay? So let's take a look at how we do that now. This is going to be surprisingly easy because here I have my likelihood, right? This is just what I computed a few seconds ago, exponent minus n lambda times lambda sum of x, right? This is the denominator here. And here I've got the gamma distribution specified in terms of the parameters a and b. I have not specified what they are right now, right? But I would fix them if I was actually doing the analysis, but I will show you where this is going now, okay? So one thing to notice in this complicated equation is that it has two parts. One is the likelihood, one is the prior, okay? That's pretty straightforward. I just plugged in the distribution, the terms of the distribution here. But one interesting thing to notice here is that several of these terms here do not involve lambda at all, right? So remember, I'm trying to get the posterior distribution of lambda given the data, right? But this gamma of a is going to be a constant number, right? This beta to the power of a, b to the power of a is going to be a constant number. This product of the x factorials is going to be a constant number. These are all the normalizing constants again for the posterior. I can just drop them, right? So we're going to just forget about all of those, and so get the posterior up to proportionality by only concentrating on this term. This is the kernel of the likelihood, and I'm concentrating on this term here, which is the kernel of the gamma distribution. I multiply them out, and you will see that it works out so simply, right? So here is my likelihood times prior, just the kernels of the distributions. And again, what you notice is that I've got one term, exponent minus n lambda, right? That came from the likelihood term. But in the gamma distribution, I've also got an exponent minus b lambda. So I'm going to have to sum up these two guys, right? And similarly, I've got in the likelihood, I've got lambda to the power of sum of x, and in the gamma, I've got lambda to the power of a minus 1. Now, if I add up the exponents in the lambda terms, right, what do I get? Let's look over here, right? I get lambda a minus 1 plus sum of x. So I'm just adding up the exponents in the lambda term. Similarly, I'm adding up the exponents in the exponential term, right? And so what you see is that we started out with this horribly complicated equation, but we dropped the normalizing constants, and we end up with the posterior up to proportionality by simply doing addition on the exponents, right? So what we end up with, though, is a form for a posterior distribution for lambda that has the same form as the gamma distribution, right? This has the same form as the gamma distribution, right? So notice that the gamma distribution, the kernel of the gamma distribution always has this form, right? So for some parameter, it's going to be a minus 1. So this should have been lambda. I'm sorry, this is theta here. I should have written lambda here, right? It should have been corrected. And I've got, read this as lambda a to the power of a minus 1, and read this as exponent minus lambda times b, Okay, so this form is exactly the form that I'm getting here in this posterior here in terms of the lambda variable, right? So all I have to do now is that I just have to represent this posterior, this kernel, in terms of the gamma distribution. So how do I do that? Right? If you just concentrate on this term here, this is giving me an updated A parameter in the posterior, right? Because the A parameter needs to look like lambda A minus 1. So what I'm seeing here is sum of x plus A minus 1. So the new parameter for my posterior distribution will be, well, you can call it A star. That would be A plus sum of x, right? And similarly, I will get an updated B parameter here, which will be whatever the update will be, and that I'll just show you in a second, okay? So let's look here, right? So the updated A star parameter for the posterior distribution will be A plus sum of x, right? And B is going to end up being B plus n, right? So what happens now is that I can write the posterior distribution in terms of A star and B star. Again, this should be lambda, it's not theta. I sometimes use lambda and sometimes theta, so that's how I ended up confusing this here. Right? So, but the important point here is pretty clear, okay? So the point is that the posterior distribution of lambda is going to have updated A and B parameters. And what are those parameters? The A parameter will be updated to A star, which will be A plus sum of x. A was the prior, the A parameter in the prior that I had used. And the updated B parameter will be B star, which will be the parameter B I used in the prior, plus the number of data points that I have. So the amazing thing now is that all I need for computing the posterior is sum up the x values that I have. When I've observed the data, I sum up all my x values, I calculate the number of data points, I know what my prior A and B are for the lambda parameter, and I end up with the posterior parameters on the gamma distribution, right? So it's really that straightforward. And I get the posterior up to proportionality, but as I mentioned earlier, I can always figure that out. This k, the constant, I can figure out later on, right? So the posterior can now be worked out, as I showed you, right? This is also an example of a conjugate case. So I'm going to quickly show you an example of how this works, right? How you would do this. Suppose this was my actual data. I have 5 data points. So I sum up these data points. I get 16 as my sum, right? N is equal to 5. So I don't actually have to do any computation. I just have to do simple addition here. I know what my A and B are, so I just do the calculation, and this is my posterior for the lambda parameter, given my prior for A and B, whatever that was, and I can always figure out the posterior now. So this is a great example for understanding how conjugacy gives you very clean posterior distributions that belong to the same family as the prior distribution, right? And if you want, you can figure out the mean of the posterior by computing A star divided by B star, etc. That's something you could report, in an analysis. That would be your updated mean and variance from the data that you have, right? So your information has changed given the new data. Okay, so we saw some examples of conjugate analyses, the binomial beta and the Poisson-Gamma, and in each case, I showed you how to derive the posterior by hand using a likelihood and a prior. And so the next thing that I'm going to show you is something very, very important, a fundamental idea in Bayesian data analysis, that the posterior mean is going to be a compromise between the maximum likelihood estimate and the prior mean. That's coming up next.